When a safety incident happens, particularly in incredibly complex and vital systems like our railways, what's the first thing that often springs to mind as the root cause? Do we immediately think of a broken machine, maybe a technical glitch, or is there something else at play, something much more human?
That's a really profound question, and it's one that's completely reshaped how we think about safety. Our initial instinct, it often is to look for the tangible, right? The mechanical failure. But the more we learn, the more we understand that the human element isn't just powerful, it's often the central piece of the puzzle.
And that's exactly what we're going to unpack in this deep dive. Our mission today is really to understand this crucial paradox. As our technology gets more robust, our machines get incredibly smart. Why do human actions, decisions, even common mistakes still seem to dominate accident reports? We're going to dive deep into human reliability, exploring how it impacts everything from daily railway operations to major accident prevention, and most importantly, how we can maybe empower that human element to build safer, more resilient systems.
So, yeah, let's start by defining what we actually mean when we talk about human reliability. Simply put, it's about how consistently people perform tasks correctly within these high-stakes industrial settings, like transportation. And if you look at the data, it's undeniable. Human factors play a really significant, often critical role in accidents across complex systems, especially in railways.
That's a truly sobering point. I mean, when you consider the history of rail accidents here in the UK, instances like Clapham Junction, Southall, Hatfield, Ladbroke Grove, human factors were identified as having a critical role in causing them. It really makes you realize it's not just about the train or the tracks, is it? It's a much broader issue.
It absolutely is. And historically, early accident models, they used to draw a pretty clear line. Causes were either purely technical failures or they were human errors, kind of one or the other. But as technology rapidly advanced and equipment reliability just soared, something fascinating happened. The estimated contribution of human error to system failure dramatically increased. We're talking about a jump from around, say, 20% in the 1960s to a staggering 80% by the 1990s.
Wow, 80%. That sounds almost counterintuitive. Does that mean people were suddenly becoming much more error-prone, or are we just getting less reliable?
Not at all, and this is where the real insight lies, I think. It wasn't because people suddenly became more fallible, no. It was because as systems became more advanced, they also became way more complex, introducing far more human interfaces. People were interacting with these sophisticated systems in new and more intricate ways. So this naturally brought human interaction, and therefore human deviation, into a far more prominent position in accident investigations. The numbers for the rail industry really underscore this. Human error has been attributed to up to 75% of fatal railway accidents in Europe between 1990 and 2009. What's fascinating here is that the focus shifted, from just the broken machine to understanding that delicate dance between human action and system design.
That's a really compelling shift in perspective. And with technical systems becoming even more intricate, placing, greater demands on human operators, it sounds like understanding this delicate balance between the individual, the equipment, and the working environment is more crucial than ever.
It truly is. Modern organizations are increasingly seeing their employees and their technology as interconnected investments. So balancing those three elements, people, equipment, and environment, for both efficient operation and, crucially, for safety, it's paramount.
Okay, so if human error is such a significant piece of the puzzle, let's really deconstruct it. What exactly are we talking about when we say human error beyond just, something went wrong? And importantly, why does it happen?
Well, human error isn't just a negative outcome, right? It's a deviation from what was intended or expected or desired. It's a departure from the plan, basically. And understanding these deviations is absolutely key to preventing them. We can classify these human failures into several practical categories to sort of better pinpoint where they come from.
Okay, so give us some examples of these classifications. Are there ones that really surprise people, or maybe where organizations often misdirect their prevention efforts?
Yeah, one practical way to categorize them involves 4 types. First, you've got mistakes. This is when you genuinely don't know what to do. Or perhaps you thought you knew, but you were actually incorrect. It's an error in judgment or knowledge.
So a mistake could be like maybe attempting to fix a complex engine part without the right training, just sort of guessing, because you genuinely didn't know the proper procedure.
Precisely. That's a good example. Next, we have violations. Now, what's fascinating about violations is that they are deliberate decisions not to follow instructions. Sometimes it's for convenience, yeah. Or maybe because the person believes they found a better or more efficient way that hasn't been officially recognized. It's not about a lack of knowledge, but it's a choice.
It's interesting. So it's like someone maybe knowingly skipping a step in a procedure to save time, even if they know the procedure exists. But you also mentioned it could be about finding a better way. Does that ever highlight maybe a flaw in the original procedure itself?
That's an excellent point. Sometimes, yes, a violation can actually reveal an underlying flaw or impracticality in a procedure. It can signal that it might not be optimized for real-world conditions. These can be really critical learning opportunities. Then we have mismatches. This happens when the task itself is simply beyond the person's physical or mental ability, or maybe even beyond what a reasonable person could be expected to do. It's about the person and the task just not being a good fit.
Right. So like placing a brand new control room operator, maybe fresh out of training, in charge of a highly complex dispatch system during a major crisis, where they simply can't process information fast enough.
A perfect example, yes. And finally, slips or lapses. These are often considered the most common type for frontline operators, maintenance workers, drivers, people like that. They are attention-based errors. You know what to do, you're skilled at it, but you briefly lose focus, or your memory momentarily falters. These tend to be less common for, say, designers or managers who typically have more time to review their work, check things over.
Okay, so is a slip then like maybe a train driver momentarily forgetting a routine check they've done 1,000 times, that brief lapse in attention? We've all had those moments, haven't we? Where you walk into a room and forget why you went there, where you send an email to the wrong person by mistake. It's that same kind of cognitive hiccup, isn't it? But in rail, the stakes are obviously, well, astronomically higher.
Indeed, the stakes are very, very different. Now, to broadly reduce these errors, we can either try to change people's behavior, which, let's face it, is often difficult, or, more effectively, we can change the environment and the system design itself to minimize the opportunities for error in the first place.
Okay, let's dig a bit deeper into why people make these mistakes. It sounds like it's far more nuanced than just saying they weren't paying attention.
Oh, it really is. We can categorize human performance into 3 main types, and each one has its own kind of associated errors. First, there's skill-based performance. These are the highly practiced, routine activities we do with very little conscious effort. Think of, say, replacing a rail clip, closing an equipment panel correctly, or setting a specific common route in a signal box. These become almost automatic for experienced staff.
Right. So what kind of errors happen with these deeply ingrained skill-based tasks? Surely if they're automatic.
Well, that's where the slips or lapses come in typically. We often see familiarity slips. This is where a frequent action kind of hijacks a similar but less frequent one, like habitually pressing the wrong lever because it's the one you use most often in a slightly different situation. Or similarity slips, where you perform the right action but on the wrong object because it's nearby hitting the wrong button on a crowded control panel, for example. You also get memory lapses, like simply omitting a step in a routine sequence you know well. Or even an association slip, where your brain makes a faulty connection between ideas, leading to an incorrect reaction to some stimulus.
That makes perfect sense. Our brains are incredibly efficient, aren't they? But sometimes that efficiency creates these little shortcuts that aren't quite right for the specific situation. Okay, what's the next type of performance?
That would be rule-based performance. Now, these activities require a bit more mental involvement. You're applying previously learned rules to specific situations you've been trained for. Examples might include evacuating a station platform using established protocols, or maybe a signal operator planning a route according to a specific set of operational rules.
Okay, so applying a known procedure. What goes wrong here then, since there's a clear rule to follow? Seems less likely to fail.
Well, errors here usually occur in how the rules are applied. You might misapply a good rule. This means you use a perfectly valid rule, but it's just not the right one for the specific situation, perhaps because it's one you use very frequently elsewhere. Or conversely, you might be applying a bad rule. Maybe you complete the task, but it has an unwanted consequence because the rule itself was flawed or perhaps outdated. And sometimes you simply fail to apply a good rule. You just ignore a rule that is applicable and valid, maybe due to distraction or perceived time pressure or something like that.
Interesting. So it's less about the physical action itself and more about the mental process of selecting incorrectly, using the right instruction from your mental toolkit. And the third type?
That's knowledge-based performance. This involves the highest level of mental involvement. It's applied to novel, unfamiliar situations where there isn't a direct rule or a practice skill you can just pull out. Think of attending an accident investigation scene, maybe. You need to analyze and synthesize new, often conflicting information to solve a unique problem. There's no script for that.
Right. That sounds like it would involve a lot of complex judgment. What kinds of errors tend to crop up there in those really high-stakes, novel situations?
Errors in this category often stem from, well, a lack of complete knowledge, high uncertainty, or cognitive biases creeping in. Two common ones are availability bias. This is where you favor a course of action just because it's the first thing that readily comes to mind, the most available solution, even if it's technically flawed or not the best fit. Imagine, say, a maintenance crew under pressure. They might quickly default to the usual fix for a track signal issue they've seen before, even if a more complex, less familiar solution might be better for this specific, slightly different, novel fault. That's availability bias grabbing the easiest mental tool.
Okay. And the other bias you mentioned?
That's confirmation bias. This can arise from things like overconfidence or maybe taking mental shortcuts. Here, you unconsciously, or maybe even consciously, look for information that confirms your existing belief about the situation, while ignoring or filtering out anything that contradicts it. So, maybe a track inspector is convinced a particular rail crack is due to material fatigue. They might unknowingly focus only on data supporting that idea, even if other evidence points to something else entirely, like maybe a specific train impact. Both these biases can lead to really faulty judgments and plans when you're faced with something new.
Okay, so knowing all these intricate ways errors can happen, slips, lapses, mistakes, biases, how do organizations actually go about reducing them? It can't just be about telling people to be more careful, surely.
Absolutely not. That's kind of the old way of thinking. The core revelation in modern safety isn't just more rules, it's a fundamental shift in design and culture. Error management really needs to be specifically tailored to the organization's context, its specific operations. The ultimate goal, really, is to develop a working environment where people can make mistakes without being unfairly penalized for the consequences, because honestly, that's how we learn. That's how the system learns. There are about 5 critical areas organizations really must consider.
Okay, lay them out for us. What are they?
First, design. Implement designs that literally prevent mistakes from happening in the first place. Error-proofing, basically. Think of railway signal interlocking systems, which physically prevent conflicting train movements. It's impossible to set up a dangerous route. Or maybe a dialogue box in a train cab that requires you to confirm a selection before a critical action is executed, like a digital, "Are you sure?" for potentially serious, real-world consequences.
That's brilliant. So proactive prevention built right into the system itself.
Indeed. Second, training. You need to ensure people are adequately rehearsed in their skill sets and knowledge for dealing with various situations, both the routine stuff and the unexpected curveballs. This minimizes the likelihood of mistakes when things get tough. Third, staffing. This is all about getting the right balance of people in the right jobs, making sure their abilities genuinely match the demands of the task.
Right, so perhaps not putting a brand new trainee, however brilliant, in charge of a super complex dispatch system on their very first solo shift during peak hour.
Exactly. Common sense, but it needs formal consideration. Fourth, culture. This is huge. Leadership needs to actively foster a supportive, healthy, and genuinely blame-free environment. When people aren't terrified of blame for honest errors, they're far more likely to report them, and that reporting is absolutely crucial for learning and preventing recurrence. And fifth, working conditions. These need to be meticulously developed and maintained to minimize factors that lead to stress, poor motivation, and low morale, all of which are known contributors to human error. Think fatigue, workload, noise, distractions.
So it really is a holistic approach, isn't it? Looking at everything from the literal design of the equipment to the psychological environment of the workplace. Okay, this brings us neatly to a more formal methodology for this, something called Human Reliability Analysis, or HRA. What exactly is it, and how does it help tie all this together?
Right. Human Reliability Analysis, or HRA, is essentially a sophisticated set of methods used to systematically model and, importantly, quantify human errors within a system. It's a powerful tool with several key merits. It provides a systematic, comprehensive analysis of all the factors that influence human performance, both good and bad. And its outcomes usually lead to concrete, practical recommendations for improvement. It's also a recognized method to support safety cases, especially when you're looking at safety-critical tasks. And importantly, its generic tools can be applied well beyond the nuclear industry, where it kind of grew up. It can provide deep insight into risk assessment in any complex sector, definitely including rail.
That sounds incredibly useful, almost like a crystal ball for predicting human behavior in a system, though I guess it's more scientific than that. But are there any downsides? Any practical challenges to using HRA?
Oh, there are. It's not magic, you're right. Some HRA methods aren't fully validated across absolutely all contexts, so you need to choose the right tool for the job. And some of the more specialized techniques do really benefit from or even require input from a human factor specialist to get truly accurate and meaningful results. Also, for certain highly detailed tasks, the analysis itself can be quite time-consuming. That might be a practical consideration if the perceived risk for that specific task is thought to be relatively low. You have to balance effort and benefit.
Understood. Resource constraints are always a factor. So how have these HRA tools evolved over time? Have they gotten better, more practical?
They've evolved significantly, yes. The first-generation tools, developed roughly from the 1920s through the 1990s, methods like THRP and HART, are well-known examples. They primarily focused on predicting and quantifying the likelihood of human errors occurring. They helped users break down tasks into small steps and consider factors that could modify performance, things like time pressure or stress levels. Around the same time, simpler expert judgment methods emerged, things like absolute probability judgment. These became quite popular in less safety-critical environments where maybe a full-blown quantitative analysis wasn't needed.
Okay, and then things got more sophisticated, moving beyond just assigning a probability number.
Yes, exactly. From the 1990s onwards, we saw the development of second-generation methods. Think CREAM or Athena. These tools went a step further, placing a much stronger emphasis on the context surrounding the error. They also looked more closely at errors of commission, that means doing something incorrectly rather than simply omitting a step or forgetting something. Though it's fair to say some of these newer methods are still awaiting full empirical validation in all areas. And for Rails specifically, there are other related techniques people use too. Things like fault tree analysis, which traces system failures back to their root causes, including human ones. There's human error, HAZOP, which is a structured, keyword-driven analysis to brainstorm potential errors. Murphy diagrams, which analyze errors by their underlying causes. And Sherpa, which is a systematic approach specifically for human error reduction and prediction. Lots of tools in the toolbox.
Okay, that's quite a range. Let's try and take all this theory and apply it. Can you walk us through how HRA might be used in a real-world rail example, maybe that emergency power restoration scenario you mentioned earlier?
Certainly. Let's do that. Imagine an emergency situation in a rail control center. An operator needs to switch a synchronization device to divert the main power feed over to an emergency supply. This emergency supply feeds two critical electrical distribution points. We can call them bus bars. Let's name them B1 and B2. They're like main power lines for essential equipment. Now, there's a detailed written procedure for doing this step by step, but in practice, operators often perform it from memory because, under normal circumstances, it's usually a pretty straightforward task. The crucial question we want to answer using HRA is this. What is the overall probability of failure of the power supply to both of those emergency bus bars, B1 and B2, if this procedure is initiated during an emergency?
Okay, so we're trying to quantify the risk of human error messing up a critical backup system right when it's needed most. How do we start to unravel that with HRA?
The very first step is meticulous task analysis. We need to break down every single human action and also every potential equipment failure that could possibly lead to that unwanted outcome, losing power to both bars. In this specific scenario, the identified steps include initiating the B1 synchronization process, patiently waiting for it to complete successfully, checking the positions of specific circuit breakers, say S1 needs to be closed, S2 needs to be open, stopping the whole process if B1 synchronization actually fails, then starting the B2 synchronization, and finally checking that B2 has completed successfully.
Right. Sounds very procedural. And after mapping out all those discrete tasks, what's the next step?
Then we move to identifying errors. For this specific example, let's focus on errors of omission, basically. Actions that should happen according to the procedure but don't. These could include the operator simply not executing the synchronization process at all, maybe under stress, or perhaps not waiting long enough for B1 to complete before moving on, or failing to check those crucial circuit breaker positions, or critically not stopping the process if B1 fails, which could then cascade into further problems when they try to sync B2.
Okay, so if someone misses a crucial check or skips a vital step, we identify that as a potential failure point. How do you then visualize how these potential failures could chain together?
That's where the human error event tree comes in. It's a diagramming technique. We map out all the potential human error, it's called them A, B, C, D, for the different omissions, and also potential technical failures, like the sync device itself failing. Let's call that 1 and 2 pounds for each bar. We map these out in a branching tree structure. This visually shows all the different sequences of events, both human and technical, that could lead to the final failure state, loss of power to both emergency bus bars. For instance, you'd have paths where the operator makes error A, doesn't start, or maybe they make error B, doesn't wait, and then technical failure 2 pounds happens.
Yeah.
It's about visualizing all the what-ifs and their consequences leading to the bad outcome.
Got it. A visual map of failure paths. And then the critical part, how do you actually quantify it? How do you assign probability numbers to these human actions and potential technical failures?
Precisely. That's the next step. Human failure quantification. We estimate the probability for each individual human failure, A, B, C, D, and also for the technical failures, 10 pound, 2 pounds. Now, generic data for typical human error probabilities, or HEPs, is available in handbooks and databases, often derived from studies in various industries. This generic data is then adjusted for the specific work conditions. Factors like high stress levels in an emergency, or perhaps the quality and usability of the written procedure, or the level of training needs can all modify the basic probability. For the synchronization device itself, let's say based on field data, its technical failure probability is estimated at Bravo 0.1 per demand, meaning a 10% chance of it failing when asked to work. By multiplying the probabilities along each success and failure branch in the event tree, we can calculate the probability of ending up at the undesired outcome, the total probability of failure for both emergency bus bars, given a demand.
Okay, so what was the bottom line result in this particular rail example? What did the analysis tell them? Did it find a high risk?
In this specific rail case study, the total probability of failure for both emergency bus bars, given a demand for synchronization, was calculated to be 0.001, or 1 in 1,000. Now, whether that's acceptable depends on the criticality, but the key takeaway, the most impactful improvement identified, was actually very practical. It highlighted the critical need for focused training, specifically reinforcing to operators the importance of consistently using the written procedures, even for tasks that seem routine or are often done from memory. Don't rely on memory in an emergency. This really illustrates how HRA can pinpoint actionable solutions that aren't necessarily about expensive technical fixes, but about human behavior, process adherence, and training.
That's a really powerful demonstration of HRA in action. It shows how a structured approach can reveal perhaps surprising insights, like the importance of sticking to the script, literally. So where does HRA fit into the bigger picture of overall safety management? You mentioned RAMS management earlier, reliability, availability, maintainability, and safety. How does HRA integrate there?
Yeah, HRA is definitely part of that broader safety management process, particularly within RAMS activities. It slots neatly into things like operational safety adjustment or maintenance procedure analysis. You can think of the HRA process less as a rigid one-off checklist and more as a powerful iterative loop that continuously seeks to improve safety performance. It typically follows about 8 general steps.
Okay, break down those steps for us. How does this iterative loop work in practice?
Sure. First, there's preparation and problem definition. This is where you understand the potential impact of failures, you prioritize where risk reduction efforts are most needed, and you clearly define the scope, what human error probabilities or HEPs you actually need to calculate. Second, task analysis. That meticulous breakdown of tasks into subtasks we talked about, specifically to understand all the potential points where human failure could occur. Third, failure identification, describing exactly how a potential human failure could impact the system's validity or safety, sometimes using guide words like action omitted, action too early, incorrect action, things like that.
Okay, so really dissecting the what-if scenarios in quite some detail.
Exactly. Fourth step is human failure modeling. This is where you develop that HRA event tree or maybe a fault tree, visually mapping out the pathways that lead to failure, incorporating the human error possibilities. Fifth, human failure quantification. That's estimating the overall failure probability using the generic data, carefully adjusted for the specific context, the performance-shaping factors. Sixth, impact assessment. Looking at the results and identifying the dominant human failure mechanisms. Which error pathways contribute most significantly to the overall risk? Where's the weakest link? Seventh, failure reduction. Based on that impact assessment, identifying concrete, practical actions to reduce the likelihood or consequences of those hazardous events. And finally, step 8 is review. Drawing clear conclusions, making specific recommendations for improvements like better training, clearer communication, maybe procedure changes, interface redesigns, and then, crucially, feeding that back into the system and iterating on the process as needed. It's a cycle.
And while the basic technique might seem somewhat straightforward, I imagine having a human factors specialist involved, especially for interpreting findings and designing interventions, is still really beneficial.
Oh, it's invaluable. Absolutely. While an engineer or a safety professional might be able to apply the basic HRA technique, specialist advice is often essential for truly interpreting the nuanced findings, especially when you're dealing with complex cognitive tasks or subtle human interactions. And crucially, they bring expertise in designing the most effective interventions. These aren't always just about more training, remember. They might involve fundamental changes to system design, control interfaces, maybe even how jobs are structured or how teams communicate.
It certainly sounds like a field that's constantly evolving, especially with technology changing so rapidly. What are some of the future frontiers in human reliability research, particularly for rail, with all the new automation and digital systems coming online?
It absolutely is an evolving field, yeah. Driven largely by the increasing complexity of modern industrial systems and, as you say, the introduction of more automation. There's an ongoing need for HRA techniques that are adaptable and can handle these new complexities. Now, historically, many HRA tools focus quite heavily on deterministic cause and effect relationships for human failure, identifying what went wrong. However, there's a really significant shift happening in research now. The focus is moving away from simply identifying and managing errors towards understanding human adaptation and resilience in hazardous or unexpected situations. This newer approach involves proactively using what are called performance-shaping factors, not just to predict error, but to model a human's ability to cope, adapt, problem-solve, and ultimately succeed, even when faced with unfamiliar or challenging situations.
Wow. So it's moving towards understanding how people succeed and adapt under pressure, not just cataloging where they might fail. That feels like a really profound and positive shift.
Precisely. It's about enabling success, not just preventing failure. And alongside that, there's also a move to address the limitations of purely probabilistic HRA approaches, especially when you're dealing with the inherent uncertainty and variability in human behavior. We're seeing the emerging use of Bayesian approaches within HRA models. These statistical methods are incredibly powerful. They allow you to estimate human error probabilities by formally incorporating context-specific performance-influencing factors, learning from new data as it comes in, and constantly refining the probability estimates over time. They handle uncertainty much better. For instance, Bayesian networks are already being used in models like SPAY-RH for assessing human reliability in nuclear power plants. So this isn't just abstract theory for the rail industry. It's part of a broader, critical trend in high reliability organizations worldwide.
This has been an incredibly illuminating deep dive. Thank you. It really brings home that human reliability isn't just about avoiding human error, is it? It's about understanding that intricate, complex dance between individuals, technology, and the environment, especially in systems like railways. It seems it's really about designing systems and processes that truly empower people to perform reliably, to succeed, not just forcing them to avoid mistakes, and ultimately building resilience into every single layer of our infrastructure.
It truly is. It shifts the entire perspective, doesn't it? From just fault finding after something goes wrong to proactively building more robust, more resilient human system interactions from the ground up.
So maybe a final thought for everyone listening as engineers, maybe as students just starting your careers, or perhaps as railway safety enthusiasts already working in the field. How might a deeper understanding of human reliability fundamentally change the way you approach design or operations or even maintenance in the railway sector? Beyond just the nuts and bolts, what if the most powerful safety innovation actually lies in truly understanding, supporting, and empowering the human at the controls? Something to think about.